Now let's look at a very important topic, which is prime and composite numbers. So before we start looking at prime and composite number, let's just understand what it really means. So here we have number 6. We have seen that we can represent it as a number of factor trees. The first two factor trees, the first and the last factor tree, are not so interesting because number 6 appear as factor of itself, which of course would continue forever. The other two factor trees are very interesting, and here we have replicated that. What we have essentially done in these factor trees is that we have broken number 6 into two of its constituents, 2 and 3. We are able to break 6 into its factors other than 1 and 6 itself. Okay, so that's what we have done here. Same in the other case. We were able to break 6 into two factors other than 1 and 6. This is not true. So we were able to do it for 6. But let's try to do it for number 3. Can we break number 3 and number 5 into two factors other than 1 and 3 and 1 and 5 itself, right? So can we do it for 3? Can you find two factors other than 1 and 3 itself, and for in case of 5 other than 1 and 5 itself? Can you find two factors? We have tried to hammer them, we have tried to run bulldozer over them, but these two numbers 3 and 5, they will not break into smaller factors. Only two factors of number 3 and 5 are 1 and the number itself. Such numbers are known as prime numbers. Very, very important. They have exactly two factors. They don't have one factor, they don't have three factors. They have exactly two factors, which is the number 1, the 1 and the number itself. Those are the only two factors of such numbers 3 and 5, and they are known as prime numbers. Let's look at number 1. Let's try to divide it into two factors. The only possible factorization for number 1 is 1 into 1, which means that it has a single factor. It has one factor, which is number 1 itself. And because it only has one factor, which is 1, therefore it does not have two factors. I cannot divide 1 into two factors, and thus it is not a prime number. So 1 is not prime because it has a single factor, which is the number 1 itself. Now, on the other hand, we have numbers such as 6, which can be divided into two smaller numbers, which can be expressed as product of two numbers other than 1 and the number itself. So for example, 6 can be written as 2 into 3. Of course, 6 can also be written as 6 into 1, but this is not so interesting for us. The more important thing is we were able to express 6 as product of two numbers other than 1 and 6 itself, and because of this 6 is not a prime number. Such numbers are called composite numbers. They have more than two factors. So in case of 6, we not only have 6 and 1 as factors, but we also have 2 and 3 as factors, and therefore 6 is known as composite number. It cannot be prime because it has more than two factors. It does not have exactly two factors, so therefore it is not prime. It is known as composite. Let's look at our number 1 again. 1, as we said, can be expressed as 1 into 1, which means that 1 has a single factor, which is number 1. Because it does not have more than two factors, 1 is not a composite number either. This is very important. 1 is a special number. It is neither prime nor composite. It is not a prime because prime numbers have to have exactly two factors, and 1 only has one factor. It is not a composite because composite numbers have to have more than two factors, and again 1 has only a single factor. It is neither prime nor composite. So remember this fact. It is very, very important. Now with that, let's move on to a game. Let's play a game. See, here we have a lady playing against a robot, and of course this lady is very, very intelligent because she is a subscriber of Examrace channel. So the game goes like this. Our lady picks up a card from this set of 50 cards. let's say that she picks up 6. Her opponent, in this case Mr. Robot, would then get all the factors of 6 for free. So we know that factors of 6 are 1, 2 and 3. So the opponent, Mr. Robot, he would get all the factors of 6 for free. This he gets for free. And he is also allowed to pick one more card from here. In the end, the person whose sum of the cards is highest actually wins. So Mr. Robot now thinks that, with his twisted mind of course, he thinks that to get highest total in my cards, let me pick the largest card. So he picks up the number 50. That's what he does. Now of course, as soon as he picks up the largest number 50, our lady, she gets all the factors of 50, which is 25, 5 and 10. So 50 is divisible by all these numbers, 5, 10 and 25. So she gets all of these cards. And at the same time, she realizes that the strategy of picking the largest card is not really working, because I am getting even large number of factors from these larger cards. So then she thinks, how do I solve this problem? Which card from among here I should pick so that my opponent would not get any factors? What are those numbers which have minimum number of factors? My friends, those are our friends, prime numbers. Prime numbers are our friends here. So she is smart, she is intelligent. She chooses a prime number. She decides to choose a prime number so that her opponent would not get any factors. Prime numbers don't have factors, only factors are 1 and the number itself. So our opponent would not be able to get any factors for free. Now which prime number she should choose? Now that's a difficult problem. Ideally, she would have to choose the largest prime number, because if she does that, her card total increases the most without benefiting her opponent. So she is smart of course, and she has studied this class in detail, so she knows that the largest prime number in this case is 47. She picks it up, and now because our opponent, he does not get any factors for free, is really confused, and lady, she is of course winning. If she continues this strategy, she would continue to win. See, one more thing that a person picking the card can do is that it is okay in this case to pick a number, a composite number as well, as long as none of its factors are present on the board. So if all the factors have been removed, then I can pick a composite number as well. Now let's see how we can find out the prime factors, right? So for winning this game, prime numbers. So for winning this game, we definitely need all the prime numbers. We need to find out all the prime numbers that we can, and how do we find them? So let's understand that. But before we do this, let's just understand two very, very simple concepts. The first concept is all the multiples of prime numbers are composite numbers, which is correct only, right? Let's take any two prime numbers, 2 and 3, okay? Or let's take two prime numbers, 2 and 2. If I write down their multiples, for example 6 and for example 4, right, 6 and 4, then because 6 would have factors in addition to 1 and 6, right, because they were formed, 6 was formed by multiplication of two prime numbers. So definitely it would have factors other than 1 and 6, and it would definitely be a composite. Similarly, 4 was formed by multiplication of two prime numbers, 2 and 2. Therefore, it would definitely have, in addition to 1 and 4, it would definitely have the factor as 2, and it would also end up being composite. So all the multiples of prime numbers, so all the numbers which appear in table of prime numbers would be composite numbers. Very, very important. Second important property is that all the composite numbers can be expressed as product of prime. So this we have already seen, right? In the factor tree, we were able to express, for example, number 12, if we draw the factor tree, then we are able to express 12 as a multiple of its prime numbers, as a product of its prime numbers. So we can do that, definitely we know. With this understanding in our mind, let's move on to the very, very important topic, and that is the Sieve of Eratosthenes. Now, finding out prime numbers is of course a very important task, and the first such effort in this direction was actually made by a Greek mathematician, Eratosthenes. Now, Eratosthenes was not really only a mathematician, he was a very intelligent scientist, and he was the first one to find out the circumference of the earth. He was also the first person to actually find out the tilt of the earth. So he was a very important contributor to several fields, and his sieve method was the first systematic way of finding out the prime numbers. So the method, we look at how it works by considering all the numbers from 1 to 100. Right at the beginning of this method, what we do is that we mark 1 as not being a prime number, because 1 is not neither a composite nor a prime, we know that. So we cancel out 1, we do not bring it into consideration at all. The method works by actually removing or filtering out all the composite numbers. So whatever numbers are really left behind would naturally be prime numbers. So that is the basic idea of this method. And we systematically go from one number to the next, marking out all the composite numbers in the process. So let's start. So the next number after 1 we consider is number 2. What we do is that we find out all the multiples of this number 2 in this list, and we say and we cross them out. See, all the multiples of number 2, for example number 4, in addition to having 1 and 4 as factors, this number 4 would also have 2 as factor, and therefore it can never be a prime number. The same is true for other multiples of 2 as well, and therefore we cancel out the other multiples of 2. So all we just say the table of 2 and we cancel the numbers out, or we look at all the even numbers which have definitely would have 2 as a factor and we cancel them out. Either way, we have cancelled quite a few of these numbers and removed them as our candidates from being the prime number. So now these are the numbers, these are the possible candidates for being the prime numbers, and the candidates are shown in pink according to our convention. The numbers which have been grayed out cannot be prime numbers, so we have already removed those from our consideration. They are the non-prime numbers or the composite numbers. Next, we move on to number 3. Now at this point, I would like you to consider this. When we reach a number, we have already looked at all the numbers below it. So when we reach 3, we have looked at number 1, we have looked at number 2 already, right? So we have looked at number 2 already when we reach 3. Similarly, when we reach other number, we have looked at all the numbers below it, and we were not able to find a factor of number 3 in those numbers. So when we looked at all the numbers below 3, in this case only there is only one number 2, and we were not able to find a factor of number 3 below number 3. Otherwise 3 would have been cancelled. So 3 is not cancelled, which means that 3 has only 2 factors, 1 and 3 itself. This means that when we reach a number and it has not been cancelled, it has to be a prime number. We were not able to find any factor of that number below that number. So the only possible factors are 1 and the number itself, and it has to be a prime number. So now we mark 3 as a prime number. So in our case, we are marking the prime numbers as blue. So we do that, and we then consider all the multiples of number 3. So the first multiple of number 3 is 6, which is already cancelled out, so we don't have to worry about it at all. Next multiple of 3 we consider is 9, and we gray it out. So we are graying out all the multiples of number 3 now, and of course we gray them out and we remove all the multiples of number 9, because they have to be composite numbers. In addition to having themselves and 1 as factor, they also have 3 as factor, and they can never be a prime numbers. So all of those 9, 15, all of those are now gone. Now at this point, let's move on to the next number and consider number 4. See, the thing about number 4 is it is already grayed out. So we know that it can never be a prime number. It is definitely a composite number. which we already know, right? Because 4 has 2 as a factor, so therefore 4 is definitely a composite number. It is not a prime number, so that much we know. What about multiples of 4? Do we have to consider the multiples of 4 at all? See, we don't have to consider multiple of 4 at all, because they would have been cancelled already by virtue of the factors of 4. Okay, so when we consider the factors of 4, we would have cancelled the multiples of 4 as well. For example, let's consider multiple of 4, which is 8. So this 8, when we consider a factor of 4, that is 2, we not only cancelled 4, but at the same time we cancelled 8 as well. So in that, what does that mean? It means that when we come to a number and it is grayed out, we can completely ignore that number. That number can never be a prime number, and we don't have to consider the multiple of that number at all. So we ignore 4 completely, we don't do any maths with it, and we move on to the next number, which is number 5. Of course, 5 has not been cancelled so far, so we mark it as prime. The only possible factors of 5 are 1 and 5 itself. We are not able to find any factor below 5. So 5 is marked as a prime number, and then we go on to mark the multiples of 5 as composite numbers. So all the multiples of 5, of course, appear below 5 as such, and they are marked as composite numbers and removed from our consideration completely. Next, we move on to number 7, and we do the same process. We mark 7 as a prime number because it has not been cancelled yet, and after that we mark all the multiples of 7 which have been left so far. We remove it from our consideration and we gray them out. Now you have to understand that we did not look at 6 at all, because all the multiples of 6 have already been cancelled when we looked at either 2 or 3. So 2 or 3 are factors of 6, and when we looked at 2 or 3, we would have cancelled all the multiples of 6 as well. That is the first thing to note at this point. The second thing to note at this point is that we do not have to go above number 10 when doing this process. Why is that the case? See, let's consider the number 11 for example, and let's understand why we don't have to do this process for number 11. The only way I can come up with multiples of 11 in this region from 1 to 100 is by multiplying number 11 with numbers from 1 to 9. Okay, so only when I multiply number 11 with numbers from 1 to 9, I can get a number which is less than 100. 11 9s are 99. If I go above 9 and I say 11 into 10, then I get a number which is above 100. So at this point, I know that when I am considering number 11, okay, I have already considered all the other factors with which 11 could be multiplied to get a number below 100. So because I have already considered and I have already cancelled all the factors of numbers from 1 to 9, I don't really have to consider the multiples of 11 at all, because those would have already been cancelled when I looked at the numbers from 1 to 9. This means that I only have to go till number 10. Repeat this process. In this sieve method, I only have to go till number 10. The speciality of number 10 is that it is square root of 100. So 100 is our last number, and I only have to do this process until I reach the square root of 100, which is 10. Numbers above 10. For numbers above 10, we would have already cancelled those numbers when we looked at the other factor of that number, which would have to be below 10 in this case. So that completes the sieve method, and these are all the factors. The pink numbers which are left here and the blue numbers which are left here are now our prime numbers. Right? So we'll mark the prime numbers blue to complete our process, to complete this convention, and this is what we get. At this point, let's now understand some special primes. So we have looked at all the prime numbers from 1 to 100. There are certain primes which are very special here. So the first such concept is that of twin primes. So what are twin primes? Twin primes are two primes which differ by 2. So the difference between those two primes is 2. Of course, 2 and 3 are not twin primes. Why is that the case? Because the difference between 2 and 3 is 1. In case of twin primes, the difference has to be 2. So here are some examples. 3, 5, 5, 7, 7, 19. They are all twin primes. The difference between these two primes is actually 2. 2 itself is a prime number, and it is a very special prime number. Why is that? Because 2 is the only even prime. All other even numbers have 2 as an additional factor, and therefore they cannot be prime numbers. So 2 is not only the smallest prime, it is also the only even prime, and therefore 2 is in itself special. But 1 and 2, they are not twin primes. Twin primes have to have a difference of 2 between them. The next important concept is that of prime triplets. Prime triplets are 3 primes which have 6 as difference. For example, let's look at some prime triplets. 5, 7, 11 are actually prime triplets. Difference between 5 and 11 is actually 6. Similarly, difference between 7 and 13, in case of 7, 11, 13 is actually 6. So these are twin primes. Prime triplets. Prime triplets are always of 2 forms. So we said that they would be P and then a number in between and then 6P. That is the form of prime triplets. The other thing, 6 plus P, that is the form of prime triplets, because this number, the last number, the highest number, has to be 6 more than the first number on the minimum numbers. The number between in here can take 2 forms. Either it is of the form of 2 plus P, or it is of the form of 4 plus P. So those are the only 2 forms of prime triplets. So that is the case of prime triplets. Another interesting thing to note about twin primes, okay, which I forgot earlier. So now we are talking about twin primes. Remember that the sum of the twin primes, except the first one, 5 and 8, their sum is always divisible by 6. So that's another important thing. Okay. For twin primes, their sum is divisible by 6 except for the first twin prime, except the first pair. And in the case of prime triplets, their difference is always 6. So that is something to note here. Now, with that, let's just look at how we can find whether a number is prime or not. Okay, so we looked at the Sieve of Eratosthenes, and we saw that, of course, one of the method is to do this process of sieve method and to find out whether the numbers are prime or not. So that is, of course, one of the methods. The second method would be brute force method. For example, if I am been given a number, let's say 97, and I want to find out whether it is prime or not, what I can do is that I can continuously divide it by various numbers, 2, 3, 5, 7, various prime numbers, until I reach the root of 97. Okay, so that's where I need to stop. I can stop at root of 97. So that process is actually simple, because root of 97 would be less than 10, so we are fine. Okay, we'll only have to go till 9. So for these smaller numbers, this process does not look too cumbersome. Okay, it doesn't look too bad. What about larger numbers? Say if I asked you to find out whether number 583 or whether number 199 is actually prime or not. In that case, we have to go quite a ways to figure out whether number is prime or not. For in the case of 199, I have to go till 15 around root of 199. In case of 583, I have to go around till root of 583 around 24. So those are the numbers till which I have to try to divide number 583 to really figure out whether 583 is prime or not. So this process quickly becomes very, very cumbersome. So finding out whether a number is prime or not is a very difficult task. It's computationally expensive. If I take two prime numbers, so in this case 583, that's exactly what I have done. I have taken two large prime numbers, relatively large prime numbers, 11 and 53, and I have multiplied them together to get 583. So if that is the case, if I take two very large prime numbers and I multiply them together, then it is very hard for me to find out whether their product is actually prime, first of all. Second, to do a prime factorization of their product. So to do prime factorization of a number which is made by two very large prime numbers is a computationally difficult task. And this fact is used in cryptography, extensively used whenever you are sending your password, your email to any server. This is the process which is used there. They are somehow using product of two very large prime numbers to secure your data. Very interesting, isn't it?